Okay, so I'm going to do an example. I call it the zipline problem, and it happens to be very similar to our textbooks, Active Example 6 3 on page 164. So, why don't you take a look at it, and then if you understand it perfectly, then you don't need to bother with this video. Otherwise, maybe you do want to watch this video. It's only 2 pages of stuff, so it's not too long. Okay, so in my example here, I've got a physicist. Her name is Patty, and she's zipping along here. So she's moving to the right. But in this example, I'm going to say she's not accelerating. So we have a equilibrium problem. There's no accelerations, and so the net force on her is 0. And we're going to actually focus in our analysis. We're going to be focusing on this place right here where the pulley is sitting on the rope. The question is, what is the tension in the rope? And you're given that you're given this angle here. It's 10 degrees, and you're given her mass. So from her mass, you're going to multiply by g to get her weight. And yeah, so what's the tension in the rope here that's keeping her from falling down? So let's draw a free body diagram. So this point right here, I guess you could say that it represents the pulley, or the spot where the pulley sits on the rope. And now, since it's a pulley, according to the law of pulleys, the tension to the left will equal the tension to the right, equal in magnitude, but not necessarily in direction. So actually on the left side, the tension is up and to the left, and then here on the right side, it's up and to the right. Okay, now these forces have to cancel, right? It's an equilibrium problem. So to tackle this problem, our next step is to decompose these vectors into x components, in other words, in the I hat direction, the horizontal direction, and y components, or in the j hat direction. So let's do that. So the left vector, it's going up and to the left, and so it gets decomposed into a y part. I'll call it t left y, and an x component, I'll call it t left x. And the right vector, the right tension vector, is also decomposed into, I call it t right x, t rx, and t, that was supposed to be, well, okay. I guess I should have called it try, but it's equal in size to the left one. So I think I can just keep calling it t left y, tly. Okay, so now let's do the trig here. The left one is equal to the cosine of the, so the x component, right, this x part here is the cosine of the angle times the hypotenuse, which is just the magnitude of t. And right, so here the magnitudes of the left and right ones are equal, so I'm just going to call them t. No need to call them t left or t right. Okay, and anyhow, the y component is t times the sine of theta. And the same business happens with the right tension vector, the cosine of theta for the horizontal component and the sine of theta for the vertical component. Really, the only difference between the left one and the right one is this negative sign, because the x component goes to the left for the left one, and it goes to the right for the right one. Yeah, and okay, just to be complete, we're decomposing the weight vector, the downward vector, and it's pointing downward, so it's negative j hat times the magnitude of the weight, which would be mg. So, okay, let's see, next step. It's an equilibrium problem. So the sum of the horizontal components and also the sum of the vertical components will be equal to 0. So for the horizontal components, we have that the left x component plus the right x component plus the x component of gravity, which by the way is 0, of course, right? This is 0 right here, that one's a 0. Anyway, we can just look at it, and by, just by inspection, we can sort of see that, yeah, these are going to cancel out. The left x component and the right x component will cancel. Now, how about the y components? They've also got to add up to 0. So the tension, the y component of the left one plus the y component of the right one plus the gravity, the weight, must equal 0. Okay, so let's plug in the things we found out here, the signs, into this thing, right? So TLY is T sine of theta. TRY is T sine of theta also. And this is FG. Now these are going upward, right? But this one here is going downward. So there's a negative sign hiding in there somewhere. Oh, here it comes. Yeah. The 2 times, okay, so these are identical, so it's 2t sine theta. I subtracted FG from both sides, and so I get that t must be equal to minus FG over 2 sine theta. Now, Fg is 600 newtons. That would be the mass of precocious Patty times the acceleration of gravity, and it's negative. And now we have a negative sign here, so negative, ooh, that's positive. And then we divide by twice the sine of 10 degrees. The sine of 10 degrees is a small number, so the end result is a pretty big number, 1,728 newtons. So compared to the weight of Patty, the rope has to have a lot of tensile strength. It's got to, hold almost 3 times as much as Patty's actual weight. So this is kind of a risky situation. These zip lines have been known to break. They can be dangerous. The rope needs to be very strong. And if you ever decide to set one up yourself, keep in mind this fact and do a little bit of math, right? Think about the angle that the tension, that the downward pull is going to put on the rope. Let's say you want it to be just 1 degree. How strong does the rope have to be then? How about if you decide you want the angle to be just 1/10 of a degree? How strong does the rope have to be now? Okay, these are important safety questions. I can tell you something. I have a friend who got hurt on one of these zip lines, and so if you ever do this, keep your physics handy. You want to get this right. Okay, thank you, and that's it for now.